So it's a pleasure to introduce Ernesto Lupercio, who will tell us about moduli and conjectural geometry.
Thank you. Well, it's the last talk, and so I'll try to be efficient and brief. I just want to do a progress report in quantum Toric geometry. But since the fundamentals are not standard yet, I will try to introduce what are the main applications of. So, classical Toric geometry we know that is made up of tori, both real and complex tori. And so you build these manifolds for algebraic varieties using the combinatorial information, the polytopes or the params, and the tori, and you end up with this variety that you obtain from the combinatorial information, or vice versa. You have the variety where those are, and then you recover the combinatorial geometry information. Anyway, the basic idea behind the field of quantum Toric geometry is to do the same, but rather than just using the classical complex torus or the real torus, we're going to use the quantum tori. We're going to build this so-called non-commutative variety out of this, given the combinatorial information, out of this quantum tori, and get these quantum spaces, non-commutative spaces. And we have these two-side row. We can go from any non-commutative space where quantum torus act densely, and actually 10, to the combinatorial information, and vice versa, given the combinatorial information, we can build up using a lot of quantum tori, the non-commutative spaces there. So now the tori here that you see there, well, you don't see the red dot, this little tori here will become quantum tori, non-commutative space. From slightly a different point of view, though, we can keep track of the parameter of the formation. So we could have started with an ordinary toric variety, say, made of tori, and we start forming it with the formation parameter, Planck's constant, except that now it's not just one number, but a vector. The Planck's constant is a vector that moves multi-parameter deformation. And we would want to do the universal deformation for a toric complexity, and that is the biggest deformation that is reached with all this combinatorial deformation and quantum tori. And so you deform the classical field into the quantum theory. And then the whole game of all these developments is that you have a lot of interesting statements in quantum in Toric geometry. So they have implications in theory, algorithm, all sorts of things. And then you want to have the corresponding statements, and some of them remain true, not all of them, but many of them, the theorem or things like that, the Harvard theorem, etc., that have combinatorial interpretations in the classical case. But now these terms, although true, have very different proofs that are not entirely trivial. Yet they remain true, and they are very interesting and have very interesting implications, therefore. So that's the basic is. And so the basic block is the quantum torus. And this acquired this name in this 1985 paper by Albert Kohn, very classical non-commutative differential geometry. So what is this? Well, in a conference like this one, people will immediately identify the quantum torus as a non-commutative algebra. That non-commutative algebra, H bar, is a real number. In physics, traditionally, bar is a very small real number. But in mathematics, not necessarily so. And you have the two generator, xy equals y. Well, not y, yx. There is this factor that appears into the 2 pi I h bar. Well, H bar is a real number. H bar complex number is also very important, but I will not treat that case, although it's important in many. Today H bar is a real number, and so we get all these quantum tori, the form, the ordinary torus. I was talking about the real torus, but we will also need the complex version. Nevertheless, H bar will remain real in all this story today. And so there is a very important dichotomy for the parameter H bar in this theory of Alan Cohen, and is that the space is truly not commutative only when H bar is irrational. When H bar is irrational, although the algebra is officially non-commutative, it is more equivalent to a commutative algebra. The couple of modules is the same of that of algebra for a commutative of models for commutative algebra rather than a non-commutative algebra. So it's only truly non-commutative, essentially non-commutative when H bar is irrational. When H bar is rational, it's essentially complex. So there is arithmetic dichotomy that is going to be again very important.
The modular space that you bring also in the same structure, why is it essentially commutative?
Sorry, I couldn't hear you.
If the modular space is essentially the same, if the similar structure, why do you call it essentially commutative?
Well, all I mean by this is that the statement, the correct statement is the algebra, this algebra is more equal to a commutative algebra if H bar is right. So that's what I call the arithmetic dichotomy. In any case, Alan Cohen observed the beautiful geometric interpretation of this algebra. That is what we will be using very much. Rather than using just the non-commutative algebra, we're going to use the fact that this is meant to be the algebra functions on a non-Hausdorff space, on a complicated space, the space of leaves of a foliation. Actually, as far as foliation goes, very simple foliation, the canonical foliation. And this non-commutative algebra is meant to be the algebra functions on the space of leaves of the canonical foliation. So the canonical foliation of slope H bar on T2R, the real two-dimensional torus, is just linear. It's just taking the linear foliation in R2, the parameter H bar, the slope H bar, and then projecting it into the torus. And this is very important for us that we're using the exponential function because therefore, the flavor of our theory is close to algebraic, but not quite algebraic, but not quite entirely analytic. It lives in its own universe. In any case, this is the canonical foliation. It's flow on the torus, and it's going to be very important for us to think of two things that are very closely related, but not exactly the same. One is the foliation, and the other is the group action of R on the torus. The group action of R on the torus. Either one of these objects, you can take a transversal circle and look at the hologram, and this is H bar. This little difference, when it comes back, is H bar, and this is the hologram of the canonical foliation. But of course, if you have a bigger dimensional torus, then the transversal thing would be a real torus rather than just a circle. And now this H bar will be a multiparametric thing. It will be a collection of numbers, not just one little number. In any case, we have the hologram group, that is what I was just describing. We can think of the group the Lie group of the two-dimensional torus acted on by the real line, but we could also think of the Lie group but now et alpha is not proper, of the circle acted on by the irrational or rational rotation by H bar. And these two group would be the same. And I say it would be equivalent categories, it would be equivalent to group points in the appropriate sense. But of course, the quotient space is non-Hausdorff. And so that's the situation which we encounter ourselves to try to model the space of leaves of this foliation. So we have these four realizations of the quantum torus. we could get the torus acted on by the real line, and modulo compact operators on Hilbert space. This would give me this algebra realized as an algebra of operators of Hilbert space, H bar. Then we could also consider just the holonomy group point, and then we will need to put this stabilization by compact operators. In any case, the group point gives me a stack is what I would call currently T2 H bar, and then and the algebra gives me its Morita equivalence class, that is the solve of the non-commuted space, or the equivalence of the capital modulus of this, or the right capital, or the other, or whatever you want. But anyway, we have the stack that is a stack given by the action of R or the irrational rotation of the circle. So we have these avatars for the quantum toric that I just described, and well, we will concentrate on the second number, on the number four, the stack. This will be our quantum toric, and we know we can recover always the non-commuted algebra from this stack. So this has a little bit more information than just the non-commuted algebra. So in any case, I can further take a logarithm. I can further take the universal cover of this one and divide R by 1 of H rather than S1 by H bar. And then I get yet another representation of the same stack, R divided by the subgroup of R generated by 1 and H bar. And of course, this subgroup is very different whether H bar is rational or irrational. If H bar is rational, it is an actual lattice inside of R. But if H bar is irrational, it's what is called by crystallography a quasi-lattice, and what we call in our quantum theory geometry development a quantum lattice. And so I will call them quantum lattice. Is when H bar is irrational, 1 and H bar generate a subgroup of R that is going to play the role of the lattice in Toric geometry. So we have this gamma will be our letter for this quasi-quantum lattices. And we have this lattice inside of R. And then, well, we have the logarithmic representation of the quantum toric. That is what we will be using mostly throughout. That is R modulo that. This is the same stack that is the quantum torus, and of course the dimension looks a little bit different, looks like dimension 1, but these represent the 2-dimensional quantum torus. I'll come back to that, you know, this puzzling 1-dimensional R there. In any case, well, the generalizations are obvious. Now I take the complex numbers rather than the regular numbers. I do that. So I get this C star modulo the rotation. And I also can do higher dimensions, but now I will get gamma as a subgroup of RD rather than just a subgroup of R. And it will be generated typically by more elements than D. Usually in what follows, the number of generators for gamma will be N bigger than D. N bigger than D. Okay. So, a quantum torus is the analytic stack equation of CD by the action of a finally generated subgroup gamma of RD. So that the vector space generated by gamma is RD. And we call that a quantum lattice, just to summarize. So that's this is summarizing everything I just said is definition 1 at the top. And this is compatible with other one's definition because if I use convolution functor, I get these non-commuted algebra up to compact operators. And the lemma is that this is a Picard stack in the sense of Artin-Rochen Verjovsky. So indeed what it has to be. It is an analytic Picard stack. So it is nice. And quantum toric form a catalog. And then I'm going to ask obviously the morphisms to be Picard stack morphisms. So, so we have a category of quantum toric. Now, but these are very, very nice, you know, there are a billion up to things, you know, exactly things. In any case, I can think of them as a billion groups or a billion Picasso stars. And the category of quantum toric is equivalent to the category of quantum lattices, whose objects are inclusions of gamma into RD, and the morphisms are linear maps that restrict to morphisms of quantum lattice. And these are linearization theory. That says that it's a little bit like the relation between toric varieties and times, where what is happening. This is the first version of that. The quantum toric in the classical case were lattices, and now in this case are quantum lattices. And then you go to the moves of the formalism of Picard stacks. Okay. In case, now I'm going to be a little bit unrigorous, and I'm just going to heuristically define CP1, quantum CP1, and I'll do it better. Just bear with me. So CP1 is equal to C star and 0 and infinity. And now CP1 H bar will be the quantum torus of that is C star modulo, the group generated by 1 H bar, union 0, union infinity. But of course, I could have gotten here weighted projective space around CP1. And here I have a freedom to get various weights. So while to get CP1, I just send Z to the minus 1. I could just get this quantum lattice, say that gamma is generated by 1 and H bar, and I can still glue these two things and obtain a CP1 that has H bar as its deformation parameter. That is H bar. So you glue these two things. Well, I have an example of P1. I use there only 1 degree of freedom, but I can add as many degrees of freedom as you will see to get the formations of CP1. Well, about the dimension counting. The dimension counting is just in case you are puzzled about T2 being a C modulo 1 H bar. That looks the dimension is wrong. But of course, the thing is that that's what the naive dimension looks like. But the homotopy type is given by the homotopy quotient of T2 by a real line. And of course, R is contracted. So this is homotopy equivalent to T2. So the periodic cyclic homology will see 2 dimensions. Even though you divided T by a quantum lattice, the periodic cyclic homology will see this thing as a 2-dimensional thing. So it kind of solves the puzzle of the dimensions, but you have to remember this fact. That there is kind of this 1-dimensional shift in the homological dimension and the naive dimension. And then, well, there's another very, very important character in this story for us. There is the appearance of complex structures that are on manifolds that are non-symplectic, non-Kähler, non-symplectic, nevertheless complex manifolds. And the thing that we are going to encode often everything on a complex manifold that is non-Kähler. So, so CP1 H bar is a nice example. Because what we're going to do is, remember, we have the canonical foliations. So what we're doing, but of course it's C star. I just want drawing the real path, you know, the canonical foliation on C star cross C star. So we have C star cross C star with the canonical foliation. And what I'm going to do when I construct CP1 H bar, the deformation of CP1 into the parameter H bar, is I'm going to holomorphically compactify the canonical foliation. So I compactify the torus as I am used to. But notice that the dimension of the torus is wrong. I mean, if I want to get CP1, I get C, I have to compactify C star cross C star. So I compactify C star cross C star with its holomorphic linear canonical foliation, and I get a manifold L H bar. This manifold has the topology of S1 cross S3. In fact, it's a Hopf surface. So you compactify C star cross C star by Hopf surface. But the important part is not so much so that you compactify C star cross C star to a Hopf surface, but that you can compactify in various ways the foliation. In various ways, in different ways, you can compactify the foliation. And of course, if you have in what I did of gluing these two shells, I chose a compactification of the foliation that foliates holomorphically without similarities the Hopf surface. So now I get the foliation of the Hopf surface, and if H bar is right, and of course the quantum torics have this thing where in the rational case, just to say geometrically what we had mentioned before, in the rational case, the torus, the ellipse of the foliation, in the picture of the chronicle foliation, in the irrational case, there is one and one and one, and each one of these is dense everywhere. But in the rational case, there are torus knots. There are so many forces, one inside is 1 plus 1, and they are dense nowhere. So this is completely different behavior. And this behavior is inherited into the Hopf surface. And I'm just doing the example of P1, H bar. So in the case of P1 H bar, we have this Hopf surface compactifying the C star cross C star. And this Hopf surface has these two behaviors, very different behaviors. If H bar is irrational, then if Y crazily around, if H bar is rational, the Y is closed off into a nice elliptic vibration section. So you are deforming an elliptic vibration over P1 in the case of the Hopf surface. You have this classical elliptic vibration, and you are deforming it into this foliation. That still is a holomorphic foliation, and of course the Hopf surface is not reflected nor heavy. So this can be generalized, of course. Take just the case of Pn minus Pn cross Pn, Pn minus cross Pn minus 1. Then you get the classical Calabi-Ekman manifolds that have the topology of S2n minus 1 cross S2n minus 1. And you get the same phenomenon. You get this foliation that floats on itself, and it's not exactly, but something, well, it is exactly an elliptic vibration. Or you get this leaf that wind crazily depending on this arithmetic dichotomy that I was talking about. In the case in which you have an elliptic vibration, well, you just get the quotient of these like that. You just the classical variety Pn plus Pn. But in the case where the leaf wind crazily because it's because now the two parameters of the formation are irrational, or one of them is irrational, something like that. Now you get a non-commutative product of not quantum P projective space, a product of two quantum projective space. Okay, now there's one more little point though, even in the elliptic vibration situation, and is that when I have two ways to, I could think of the quotient in two different ways. In the rational case, the leaf becomes an elliptic vibration, and the leaves really wind on themselves. The C universally covers the elliptic curve. And if I divide, well, I get P1. But if I remember that it was C acting and not an elliptic curve, then I get P1 together with a jerk. And this is already non-algebraic, it's already all minimal, this is a non-minimal structure. And this jerk, you can think in terms of quantum theory that you turn on the jerk of the theory, or do you add a non-commutative degree of freedom to P1? But it's totally canonical. That's what the category of toric varieties, and the category of toric varieties with these canonical jerks turned on are equivalent. So I can think that the toric variety always secretly knew it's the jerk that was going to be turned on. And in this case instead. And the thing is that more generally, every toric variety, this is in the paper of Meersseman and Verjovsky 2004, every toric variety has something like a Calabi-Ekman name. It's called a Calabi-Ekman. And this picture you can reproduce for compact projective Toric varieties are more general, LB, etc. And but of course, you have to choose whether you remember the variety with the gel or without the gel. And I'm going to remember with the gel because if I forget the gel, I don't get a modular space. Remembering the gel of the Toric variety, the singularizes the modular space and allows me to have a nice modular space of Toric varieties. So, that being said, we call these gels, we call them, the datum for these gels, we call them a calibration. Because we want not only topological gel, but we want gel that we cannot, so we will call it a calibrate. We will calibrate the Toric variety. So, I'm using the rational case. Well, likewise, you get the Toric variety together with the gel. And this LBM manifold can be thought of, if you have a Toric variety, as the two-fold homotopy complex cover of the Toric variety. It can be thought of like that if you want, by universal properties or whatever. And now, again, in the case of rational parameters, we will get this classical Toric variety. And you may decide to forget the gel if you're thinking of one of it, but if you're thinking of the modular, you better remember the gel. Okay, so, but so let's think of a quantum torus that is CE modulo gamma. You may want to remember the generators of gamma or to forget them. If you forget the generators of gamma, you get an uncalibrated quantum torus, a normal quantum torus. If you decide to remember the generators of gamma, then you will get what we call a calibrated quantum torus, and that's easy to report. Especially in the irrational case, it makes no difference. But in the rational case, it's very important. So anyway, we define the category of calibrated quantum lattices. And we have this J little thingy there that seems like a funny combinatorial thing that just adds more J. So the indices that are not in J, you can think of them as just mark points on the line. You can think of them as mark points on the line. So you have the gamma and the extra J thing is mark points in gamma. And you may want to have no mark points whatsoever, or to have some mark points in gamma. And I'm marking this point because, again, this is going to be the analogous of the marking points and curves among the spaces later on. In any case, we have the notion of calibrated quantum lattice. So you mind these days, typically dense lattice, but a calibrated quantum lattice. So if this is RD, and you typically find this kind of dense lattice there, gamma. And no longer lattice, quantum lattice, quasi lattice. But a calibrated one is taking an enormous lattice in higher dimension. You know what I mean? Taking an enormous lattice in higher dimension. And remembering the map H that has exactly the image gamma. So you not only remember gamma, but you remember a calibration of gamma. And once you do that, and that's the meaning of H. You have a category of calibrated quantum lattices. And now, well, here you have an example of a morphism. And the theorem of course, the category of quantum calibrated quantum toric is equivalent to the category of calibrated quantum lattice. Just for a moment, I will read the theorem that I mentioned before about quantum toric as Picard stacks. And well, here you have a nice example that explains how this makes these symbols meaningful. This automatically makes symbols like this in the monomials of the theory. It makes the meaning of this symbol is explained by morphism of calibrated quantum toric. So now your monomials can have a rationality. sent to all these birational. Now you have monomials with positive irrational form. And that's okay. And this explains what this. I put this potential marks and z goes to z square root of 2. But because this is the minimum, z goes to z square root of 2. And now we have these monomials with rational exponents. Okay, it makes perfect sense. No problem. This is a morphism of quantum toric. Z goes to the square root of 2. It's a good character for this quantum toric. Okay. Well, now you can have the obvious quantum fan for CP. You can have the fan for CP1, but now you can put gammas there, and you will get CP H bar. But now, right, you get this to the raise with the gamma, and this is what should be called a quantum fan. So this is what a quantum fan looks like again. You have a quantum lattice, and you want the fan lives on the quantum lattice. The fan lives on the quantum lattice, but you need in these mark points that I have, you need at least one mark point at every rate, and then maybe other mark points. But you need at least one mark point to have a Planck scale, or because in the past you could take the choice primitive. Now there's no such thing. You have to decide. So, and this is for the quantum field, talking about a Planck scale. But anyway, just mathematically just choosing a mark point at every rate. So when you do that, and this is the way a quantum fan looks like behind my scale, and this is a calibrated quantum fan. It's like a quantum fan, you know. But now you remember H. And H is going to the calibration. Is going to be the deformation parameter for the moduli space. H, the calibration. So the moduli space is going to be the set of H's that is going to be an algebraic, a semi-algebraic set. The possible H's form a semi-algebraic set. And these semi-algebraic sets are arbitrarily complicated, as one can prove. You can get it defined in your pattern. And but it's a semi-algebraic set, a set of H's, and then you divide by the obvious symmetries, and you get the modular space of toric objects of all five. So the modular space that the modular space will be the modular space will be the set of H's modular somewhere. And this will be a complicated semi-algebraic set. In dimension 2, you still can say something about it. You know dimension is hard and to describe semi-algebraic set, but then there is some equivalence in there. And this will be the modular space of but the modular space, I should have said, will have D and D. So D in N is the dimension to the N, R to the D. And D is the combinatorics of the fan. It's a poset, the combinatorics of the fan. D in the classical modular space of curves, it was MGN. D plays a role of G. It determines the topology, is the genes of the real answer. It's just the poset of the function. D plays the role of G, and these play the role of A. And there is a nice case where you have exactly as many mark points as grades. So, so you know that this is DD, and then it's only one parameter, and that's almost NN. So in that case, that is the simplest. So you can mark more points, and this is important for our meditations on the logarithmic transform and all this stuff. But at the simplest level, you do just NN. So you are in the situation. You have an integer that mark points on the fan, and the combinatorics of the fan. So you have a topological invariant and an integer, and the modular space is labeled like that. And of course, gluing the modular spaces as we decrease the complexity of the poset will produce a modular. So there will be the participation of the molecules. Okay. So, anyway, I haven't even defined what is a, now I have defined what is a calibrated quantum fund. But to a calibrated quantum fund, I have to tell you what is the quantum Toric variety that corresponds. And all I'm saying in this one is that how do you do it for a cone? You can first you straighten the cone, you do that, and then you bring back the shape of the cone, and then you have and this U is a quantum Toric stack that has as a dense subset a quantum torus is stacked. It's not a variety, but it is a non-sequential stack. By no means a variety, but you can think of it as the basic quantum Toric variety or quantum Toric stack associated to the cone. And well, that's the form, the explicit form. But you can imagine what you do. And now you can imagine what you do. You just glue them with the instructions of the fan. The fan tells you how to build these various objects. And because we have set up everything to work, it works. And then you can define for a quantum fan. It doesn't need to be complete fan in general. Doesn't even need to be implicit, but then you have to be careful. Today I'm going to mostly intuition, otherwise it's hard. But you can do it for non-simplification. Antoine Boivin has written a paper with this. Our paper with simplification and one generalizes it to non-simplification case. And but you can do it. But this is the simplest version. To every quantum fan, you get one of these stacks, the quantum Toric variety. Okay, and again, in general, the calibrate, if you remember H, it's calibrated, and then you can forget H and do the stack of just dividing by gamma, not dividing by the action as here. You know, here I'm dividing by this action here, but you could divide by gamma here. And so you get the calibrator, and this is a property that explains what you would expect, that they differ by a jet. And a combinatorial computer with jet. Nevertheless, turning on this jet makes transform things from algebraic into non-algebraic at the level of the two-pole Homological. So we have the non-algebraic complex manifolds playing into the picture. Here, this is a simple example. Let me just describe. Maybe this is more easy to imagine, you know, it's because now it's a P2. What happens with quantum P2? Well, you know the fan, but now you could have the third way to have this direction AE rather than a rational direction, you also have a rational direction AE or rational. And then when you do the calculations, you get these three cones stacks, and you can glue them by things that are like these symbols at the level of the quantum toric, at the level of characters of the quantum toric. And then here you see now it's a two-dimensional quantum toric, so you are allowed to have, it's not even all that complicated here. You are allowed to have this kind of symbols and this kind of symbols as gluing things for the quantum toric. Just like we used to have this kind of symbol, and you glue, and then you get the quantum toric associated to this file that could be an irrational. And here there's no more mark points than those on the race. And now you go and prove that the capital calibrated quantum Toric variety is equivalent to the capital quantum Toric parts. Calibrated Toric parts in the sense of the calibrated Toric quantum parts. Now you can do quantum geometric invariant theory. You do the gauge transform to the H, and you get an A. You do the gauge transform to H, you get an A. That's the definition of the gauge transform, and the definition of A, the gauge transform of H. with A, and with combinatorics, you define, as you would expect, an open set, semi-stable points, S, and then you divide by the action A, of H, or A, the gauge transform of H, and then you get some stacks there, S mod A. So you get a stack that is a well-defined stack. The combinatorics works well with the action. The dynamics of the action is compatible with the combinatorics of this open set of stable points. It's a dynamical system. Just a description of a dynamical system. And, well, it turns out that this stack is exactly the, so this is another definition we made of the quantum toric variety that doesn't use shouts, but rather is kind of geometric invariant theory kind of definition. Or this other definition of defines an open set and an action and you divide. So this is another way of defining the quantum toric variety. And well, if you take rather the transversals, you can get a nice you call them blue points. You can make the blue points small, just like for the quantum dots. Just taking the transversal for the foliation, the respective foliation. If you just take, but the point is that if you take the group action, you get the calibrated quantum toric variety. If you just take the foliation, the following is groupoid of the foliation, then you get the uncalibrated quantum toric of the new foliation. The foliation doesn't remember. And as for but you see, this was this S. That's combinatorially defined. But you can retract this S into a nice compact complex manifold. And this is the generalization of the Cavalier. So this is it's a one possible definition of this manifolds in this one. You just you get the shortest point in every leaf of the foliation to the origin, and then you get N, that is a compact complex manifold, and the complex structure encodes the whole situation. So even if you mark more points, the topology of N will change, but the complex structure will transform, and the complex structure N will encode the situation. So we have some interesting conjectures looking at it. They're not ready to say because I don't know if they're true, but we believe some very interesting properties of complex geometry can be investigated in this direction. In any case, the foliation you get on calibrated and solid, and the calibrated is you get the back. Okay, a quantum toric variety, a quantum toric stack is with delta complete is scalar and only delta is full total. This is something that you want to have and see. So some of them are scalars, and the ones that are scalar are exactly the ones that could follow. Irrational pointers at that, possibly. And we use this result of Meersseman to put this beautiful fact. That is expected of you. And but now, unlike classical toric varieties, now I'm going fast. I'm sorry. Unlike classical toric varieties, now we kind of form. Now we're really a toric variety, not as conjectural. We're really, but now we kind of form a toric object because we kind of form the quantum torics. And intuitively, I may explain the relation more a little bit more carefully, but intuitively you can imagine that you form the holomorphic foliation. It's a little bit more subtle than that. Nevertheless, you can imagine, well, now you have these modular spaces, and of course the finds or polytopes that have lots of symmetries will be orbifold points of the modular space. And the modular space will be an orbifold. And sometimes it will be even a complex orbifold, or almost a complex orbifold. I'll explain what I mean by that. So anyway, you have this modular space of Toric things. You fix the complementarities of the function to begin with. Once you start compactifying, you start changing the complementarities of the function. But it's like fixing the genes for the modular space. You fix the complementarities as opposed. And so you get these modular spaces of Toric stacks. And again, the orbifold points are defined that have lots of symmetries. But there is also the modular space of polynomials on the complex manifold, on the LBM manifold. And that undoubtedly is a complex orbifold, and they have to relate, surely so. Not always, because not all of them come manifold. Some things have to be even, and you can't have too many points for this to work. But in that case, if you have these numerical coincidences, then your Toric modular space is essentially a complex orbifold, except for this kind of non-complex part. And this is something that is going to return to us in the compactivity, in the big moduli conjecture. So that's that. This is a twistor bundle. In any case, this is just an obvious condition that I have to ask between H and D, the combinatorics. And I have to ask that there can be finds with that combinatorics for a given H. If I take H, there's some combinatorics that can be realized, some that cannot be realized. It's not entirely obvious, but in higher dimensions it starts to matter. Not into the So in higher dimensions they start to matter. So we call admissible the combinatorics of HD admissible. There can be realization of the combinatorics. This is already a super hard problem, but I will because this determines the structure of all the H's that are admissible with D, omega D at the top. And this gives algebraic, semi-algebraic inequality, so it becomes a semi-algebraic set. And just the equations are not enough because it's connected, so it's a connected component of a extremely complicated semi-algebraic set that cannot be put on a computer because it's extremely unstable. This can also be proved that, well, it's the obvious thing, you know. Just moving a little bit more could completely change the combination, the problem. So it's not, you cannot put this on the computer. Anyway, omega D is an open connected semi-algebraic set of R, D, M, and D. And this is the topology of the modular space of Toric objects of fixed combinatorial type D. And of course, now we're starting to work with Rita Jimenez and Ernesto on trying to get homological stability, these kind of things, like the modular spaces admit these kind of questions from pure topological nature for the modular space. But this is the topology of the modular space. Well, I already said this, it is a connected semi-algebraic subset, and a very delicate one of that. And more interestingly, we get some examples for you can get B K's S3, 1 and KDN, 1. You can get arbitrarily complicated groups, and you can study these modular spaces. And you can study these modular spaces. You can get arbitrarily complicated groups, and so the problem of computing the modular space in general is the problem of computing groups of homology and words, which you have. But you can start to choose families, sensible families, and try to understand the problem of homological stability for the modular space. Of course, we understand very well the symmetric group and maybe JL and ZN, but these are the models of it's a hard group to even, you have to choose from the following to think of homological representation are max and dice, varieties, so the theory admits non-simplified funds. I already said that it's a non-trivial generalization, but it can be done. We understand the ups and low downs and more general birational morphisms. Now we have managed for morphisms because in the past, well, it was only a rational thing. We have these secondary funds, and we have the big modular space. All these tools are indicators that we could perform. We are starting there with the minimum model program for quantum Toric varieties. But well, we have now all the basic ingredients. I won't go. Let me just do a little bit of an example for compactification. The compactification of quantum projective spaces looks like of dimension D, looks like a tropical object. It looks like AI positive in RPD, and then acted on by the symmetry. This is what the compactification. Because of course, just like MGN, compactified by generating and having simpler M or lower index MGNs at the boundary. Exactly the same happens here. MGN degenerates to simpler or smaller posets, and you put them at the boundary, and then you compactify the whole of the space. The main thing that you have to check after you do this naive compactification is that there is a universal family, and you check that there is a universal family, and there is. So this is what MD looks like, and of course it's easy to you say, well, I just let it close and I compactify. This is MD for quantum PD. This modular space has an irrational points of the weighted projective spaces. And irrational points are truly non-commutative projective spaces. We have the weighted projective spaces that are the rational points. The irrational points are truly non-commutative projective spaces. And it's an open thing. Well, you close the thing. Here you have a universal family in the open thing. And well, you close the thing and it works. The boundary is you get this MD minus 1, you know, none of the vertices MD minus, you know, you get this simplicial stratification by MD. And it's a nice simple example. Of course, we know that omega D will be astoundingly complicated in general. I mentioned pi and higher will be monstrous. And but the same picture still holds. This is what I just did. These are the various degenerations and the various modular spaces that appear at the boundary. Here, there's a funny stabilization. There's a little experiment, I don't know what it is, where you have this at the boundary. You really don't quite get MD minus 1 exactly. You get MD minus, you get lower dimensional projective space cross a canonical torus, quantum torus, non-complex. So you ignore the canonical, you contract, you take the suspension away, you ignore this part. If you identify two Toric quantum Toric varieties when you multiply by a C Boivin universal quantum torus, then it really works. It's pretty long. But here are the various degenerations that are the analogous when you're constructing the limbo for compactification from here. This is the same story but for other case with the combinatorics of the part. So you do that, and you get a universal family. The various open families look well, and you get a universal family, and so you get the correct compactification. But now you want to get all Toric objects in only one module space. and is can be done. It's the big Toric moduli conjecture was done by Homological, and so he gets all the Toric objects in only one moduli space. So you have the blocks and flow walls, everything is there in just one big moduli space, and then it has a universal function. It's humongous moduli space, but it can be conserved. And that's it. Well, thank you very much.